One Dutch company, ASML, sells a machine so complex it costs more than $350 million, ships in pieces across multiple cargo planes, and decides whether Apple, Nvidia, Intel, and TSMC can keep making chips smaller. This is not just another supplier in the semiconductor chain. ASML's extreme ultraviolet lithography systems are the bottleneck behind the most advanced processors on Earth. Without them, the tiny electrical cities inside phones, data centers, cars, and weapons systems stop shrinking. And that gives a company from Veldhoven, Netherlands, an influence usually reserved for states. Welcome to the Machine Notebook. In this episode, ASML's light machines become the choke point for every chip powering AI, cars, and weapons. Draw the chip industry as a world map of interlocking gears. Taiwan spins with TSMC fabs. California spins with chip designers like Apple, Nvidia, and Qualcomm. South Korea spins with Samsung memory lines. Germany spins with mirrors from Zeiss. San Diego spins with laser systems from Cymer. And in Veldhoven, in the Netherlands, a small pin holds the center. That pin is ASML. ASML does not design the iPhone's brain. It does not brand the graphics card. It does not run the cloud server. It builds the tool that lets all of them become smaller and stronger. By the 2020s, every leading-edge chipmaker needed ASML's most advanced machines. A single missing lithography tool can delay a fab worth $10 billion. One Dutch company became the narrow bridge between human imagination and silicon reality. In 1984, ASML was not an empire. It was a risky spin-out from Philips and ASM International. Its first home was not a gleaming headquarters. It was a cluster of temporary buildings near Eindhoven, beside Philips' research world. There were only a few dozen people at the start. The ceilings leaked. The company was small. The enemies were enormous. Japan's Nikon and Canon dominated lithography, with machines already trusted inside the clean rooms ASML needed to enter. America still carried the memory of its own chip-making power. ASML's first stepper, the PAS 2500, arrived in 1985. It had to sell into factories where one bad alignment could destroy an entire batch of wafers. Its early tools were not magical. They were survival machines. Each one had to print circuit patterns a little cleaner than the last. Each customer visit mattered because a chipmaker would not gamble a production line on romance. Each sale bought time. Each failure threatened extinction. The company's weapon was not scale. It was obsession. A pattern had to land on silicon with the discipline of a watchmaker and the force of an industrial press. Lithography is shadow puppet printing at atomic scale. Start with a mask. The mask holds the blueprint of a circuit, usually a quartz plate patterned with chrome, like a stencil for a city. Send light through it. Shrink that image through a lens system, often by a factor of 4. Land it on a silicon wafer coated with photoresist, a light-sensitive chemical film. Where the light hits, chemistry changes. Where it does not hit, chemistry waits. Then the wafer is developed, etched, cleaned, and layered again. One layer becomes roads, another becomes gates, another becomes wires. A modern chip can carry tens of billions of transistors. Each transistor is a switch so small that millions could fit on the period at the end of a sentence. The problem is brutally simple. Smaller lines make faster, cheaper, more efficient chips. But light behaves like a brush. Engineers describe the limit with a hard equation. Resolution depends on wavelength and numerical aperture. A krypton fluoride laser at 248 nanometers could only be pushed so far before tricks became mandatory. Use a thick brush and the lines blur. To draw smaller circuits, ASML had to make the brush thinner, straighter, and more obedient than physics wanted. For years, the industry used deep ultraviolet light. The wavelength was 193 nanometers. That was already far smaller than anything the human eye could see, but the chip makers wanted lines even thinner. The old path was to find a shorter wavelength. That path was slow, expensive, and full of dead ends. Then Bern J. Lin, working at TSMC, pushed an almost childlike idea. Put water between the final lens and the wafer. Not metaphorical water, actual ultra-pure water. Air bends light one way, water bends it harder. That extra bend let the machine focus tighter. A glass of water became a weapon against the end of Moore's law. ASML moved fast. Martin van den Brink and his engineers backed immersion lithography when the industry still argued. By the mid-2000s, immersion tools extended 193 nanometer printing far beyond its expected life. The machines drew smaller lines by tricking light into behaving as if it had a finer tip. But water was only a bridge. On the far side waited a darker, stranger machine. Extreme ultraviolet light does not come from a lamp. ASML's EUV light begins as molten tin. Tiny droplets fire through a vacuum tens of thousands of times per second. A laser strikes each droplet once to flatten it. A second laser strikes it again to make plasma hotter than the surface of the sun. From that flash comes 13.5 nanometer light. Ordinary glass would swallow this light. So EUV cannot use normal lenses. It must bounce from mirror to mirror. Those mirrors, made with Zeiss, are polished so perfectly that if one were enlarged to the size of Germany, its tallest bump would be only millimeters high. The whole path must stay inside a vacuum. Dust becomes a boulder, heat becomes a moving floor, vibration becomes an earthquake. This is not a printer anymore. It is a cathedral for light, built to draw a city smaller than bacteria. The EUV machine did not arrive like a clean breakthrough, it arrived like a siege. For years, power was too low, uptime was too weak. The tin source sprayed debris. The mirrors had to survive invisible punishment. The machine had to align moving wafers with accuracy measured in atoms. Customers waited, costs climbed, suppliers strained. ASML's supply chain grew into thousands of specialized companies. One missing valve, sensor, mirror, or laser part could slow the whole beast. Martin van den Brink became the face of the engineering war. The company bought Cymer in 2013 to secure the light source. TSMC, Intel, and Samsung pushed, funded, doubted, and returned. Then geopolitics entered the clean room. The United States pressured the Netherlands to restrict advanced exports to China. EUV machines were blocked from Chinese fabs. A tool built to shrink circuits became a border checkpoint. The smaller the line became, the larger the political shadow grew. Peter Wennink led ASML through the moment when the impossible machine became essential. EUV was no longer a laboratory promise. It was printing the most advanced chips on Earth. ASML did not make those chips. It made the stencil that decided what those chips could become. A faster AI server begins here. A better phone camera begins here. A modern car's control system begins here. A weapons platform begins here. The company's headquarters in Veldhoven became one of the most strategic industrial sites in Europe. In 2023, ASML reported $27.6 billion in net sales, and its order book showed how far demand ran ahead of supply. That same year, the Dutch government tightened export rules after pressure from Washington, making lithography a matter of state policy, not just factory planning. The bottleneck was not oil, steel, or shipping lanes. It was light. Now ASML is pushing high-NA EUV, with the first EXE5000 system shipped to Intel before the end of 2023. The question is no longer whether humans can draw smaller electrical cities. The question is who gets the machine, who is kept from it, and how long physics will keep opening the door. The bottleneck was light. A beam shaped in Veldhoven now passes through the balance sheets of TSMC, Samsung, and Intel, through export controls in Washington, and through the strategic calculations of Beijing. ASML's machine does not look like power in the old sense. It looks like mirrors, vacuum chambers, and decades of patient engineering. But without it, the tiny electrical city stops getting smaller. And in the next chapter of technology, whoever controls the light may help decide the shape of the world it illuminates.